Okay, yeah, so I couldn't decide what to talk about, so I'm going to just give you an overview of things I've been thinking about and working on. Um, they are all related in some way or another to spherical harmonics. I might not get through all of them, and that's fine. Feel free to interrupt with questions. I can't see the participant list, so just blurt it out. It's fine. This is basically the 1, 2, 3, 5, 6 things that I've been thinking about recently. They're all related to this thing that I've been working on for the past several years, which is mapping the surfaces of stars, mapping the surfaces of planets, trying to understand what we can learn from light curves, spectra, and other unresolved data sets about the surface and surface processes. And so I'm going to start talking about some information theory aspects and then go clockwise through these. I'm going to talk about ensemble analyses and how it's very hard to learn something about, say, a single stellar light curve because there are so many degeneracies on the problem. It's much easier if you have lots of them and you can analyze them together and try to understand what the covariance across light curves is telling you about the statistical properties of that ensemble. And then I'm going to switch gears a little bit and talk a little bit more about planets and mapping planets and how if you observe phase curves of planets in the optical and you're measuring actually reflected light off the surface of the planet from the star, that's a well-posed problem in a sense, because the fact that you have a night side that's not contributing flux breaks a lot of the degeneracies on the problem. And so those light curves encode a lot more information about the surface than thermal light curves. And then the thing that I'm working on right now is modeling transits across oblate stars. That there is an exaggerated GIF of the oblate Earth, but the idea is the same. How do you model a transit light curve across a star that's not spherical? And what science you can learn from that? I'm also thinking about extreme precision radial velocity systematics, particularly in how star spots and other features on the surface of the star can introduce noise in the radial velocity measurements when you're searching for planets, and how to combat that. By the way, that's the Earth in Doppler shift. I mean, again, not really realistic, just a fun example. And then finally, some thoughts I have on reproducibility in science. I've been thinking a lot about, how to make papers open source, how to make them as transparent and reproducible as possible. And so there's a LaTeX package that I'm working on that I love people's feedback. Okay, so, and again, I probably won't get through all of these, and that's fine. So information theory. I want to do a quick pop quiz, and that quiz is, say you observe this light curve with TESS or Kepler or whatever, and it's a star, and you can see that it's periodic, the period's 1 day or whatever. My question for you is, if you were to try to figure out how many star spots this star has based on just this light curve, how many do you think this star has? So your options are 1 through 6. Those maps down there are synced to the light curve. You'll see that they have 1 through 6 major dark spots. Maybe type into the chat your number, which you believe to be the answer, the correct.
And only one of those is correct. Is that right? One of these is.
I have not. One of these was used to generate this light curve, but I have not told you anything else. And Hog, obviously, spoiling it for everyone.
Wait, can you read the chat or
I can read the chat, yeah.
You can read the chat. Okay, great.
Dan says 42. Adam says all of them, 0 infinity. You guys aren't good sports. Come on. Okay, Trevor said 2. Drummond said 3. Thank you for playing along. If you said 3, which I think Drummond did, and a lot of people did too, you are correct. But if you said 5, you're also correct. And in fact, any number that you typed into the chat would have been correct. I don't know about 42, but probably. The point being that if you compute the flux emitted towards the observer by any of these 6 maps, you get exactly the blue curve. Exactly, right? Even if you were to have a measurement at infinite signal to noise, you would not be able to tell the difference between these curves. And this is something that I've talked about a lot in STARS meeting and probably in lunch talks past. But the problem is so degenerate that you cannot learn simple things like how many spots does this star have.
And that's literally true at machine precision, because that's a very strong statement.
It is literally true at machine precision. There are caveats. You'll see that there's some, like, these aren't literally just uniform stars with dark spots on them. There's some background inhomogeneities. That's what allows me to like cheat and actually get exactly the same light curve for all of these. But there's no reason we'd expect stars to have perfectly uniform photospheres with perfectly uniform circular dark spots either. And so
Will has something to ask too.
sure, yeah, go ahead.
So I think I'm probably just anticipating things that are coming because I've read your paper, but I'm going to ask, if I picked all those images up with my little grabby mouse hand and rotated the inclination a bit, you could play this trick again, right? But you would need to change the spots pretty dramatically.
Yes,
to match.
Exactly.
So since we know physically that inclinations are isotropically distributed because other stars don't care about Earth for some strange reason,
right, we
can get a statistical, okay, great. And I just gave the rest of your talk. I'm sorry.
Yeah,
okay.
No, that's fine. I mean, great. That's exactly it. So I will talk about that. And the punchline in a few slides is going to be that you can't learn things like this about individual stars. But because these degeneracies depend strongly on inclination, you can learn things about ensembles of stars. Yeah, but very well put. That's exactly correct. So there was this a figure from my paper where one of the ways to understand the degeneracies at play is to think about the decomposition of the operator that takes you from the surface map to the flux. And because I'm doing this with spherical harmonics, that's a linear operator, and so things are well behaved, I can decompose it into 2 parts. Into a part that contributes information to the flux and a part that doesn't. And so in linear algebra speak, that would be the null space is the part that doesn't contribute. And then the pre-image, the image, there are a couple different ways of saying this, but that's the part that contributes information to the flux. So here there are 3 stellar maps, the 1 spot, several spots, and then a really absurd, like message written by aliens on the surface of a star. And below each one is the light curve we'd observe at a fixed inclination. I think this is like 60 degrees. You can decompose this into the stuff that's contributing to the flux. That's the central column, the pre-image. And the stuff that isn't contributing to the flux, the null space. And you'll see that everything is linear, and so the maps add across the rows, but the light curves also add across rows. And so you'll see that the pre-image gives you the exact same light curve because that's the stuff that's contributing to the light curve, while the null space gives you exactly 0 by definition. And unfortunately for the light curve mapping problem, most of the information in all these cases is in the null space. It's in the wrong place. And so the only thing, the cool thing about the pre-image is that another way to think about it is if you do like least squares fit or like posterior inference with a completely uniform prior in spherical harmonic space, it also works if you have a completely uniform prior in pixel space, you get the pre-image. And so if I naively go and fit the light curve of the top light curve with a spot model or with a surface map model of some sort, provided I have a uniform prior on the values of all the pixels or all the spherical harmonics, I will get the stuff in the central column. If all you have is 1 spot, you can kind of identify where it is and roughly how big it is, but that quickly breaks down if you have more spots. And it becomes impossible if you're trying to recover high resolution information like, an alien message. Most of the information never makes it into Light curve in the first place. Just to summarize this, right? So like, even if you see a really nice light curve and it's very complicated, counting the number of oscillations, measuring the peak to trough flux difference cannot tell you about fundamental things like how many spots, how big are they, etc. Because it's too degenerate. However, so as Will mentioned, the one thing that works is to ask this question for many stars at once. And you'll notice that, so here's an example of, I think 50, a lot of light curves of stars that are statistically similar. Each one of these stars has the same number of spots at the same latitude. It's just where exactly in longitude they are is different. And it's just drawn from some isotropic prior. Even though these stars are all statistically similar, their light curves are very, very different. And so that's really good because suddenly I have samples from some statistical distribution that all have very different degeneracies because they're observed at different inclinations. And so together, these light curves encode a lot more information about, typical spot size, typical spot latitude than any individual one could. And so armed with this knowledge of like ensemble analyses being the way to go here, what I've been working on for the last year, and I'm still working on it now, is coming up with a Gaussian process that captures the variability due to spots. And the cool thing here is that I was able to figure out like a closed form expression for the covariance of a Gaussian process conditioned on like statistical spot properties, like typical spot sizes, typical spot latitudes, typical spot contrasts. And the cool thing here is that because it's a closed form expression, it's very fast to evaluate. But even better, because it's a Gaussian process, I now have a likelihood. I have a likelihood function. Yeah, closed form, many exclamation points, hog. I now have a likelihood function that I could use that automatically marginalizes over all the unknowns, which are exactly where an individual spot is or exactly how big an individual spot is. It's marginalizing over all that, but it's conditioned on mean spot size, mean spot latitude, variance of spot size, etc. And so this makes it very efficient to do these kinds of ensemble analyses, to learn things about many light curves at once. This is from my paper. So I did a bunch of synthetic ensemble analyses on thousands of light curves. You can actually learn things like the active latitude almost exactly. It depends on the signal to noise data and how many light curves you have. But that information is there. You can also learn, surprisingly, the inclinations of individual stars to something like a few, maybe 10 degrees. Typically, you can't do that from a light curve, but conditioned on the fact that you believe all the stars in your sample are statistically similar and have similar active latitudes, you can get very good constraints on stellar inclinations. And so all of this is part of me thinking about how to understand surfaces of stars for its own sake, to understand stellar magnetic fields and stellar activity in general, but also to better understand the systematics contributing to like extreme precision rate of velocity measurements, transit transmission spectroscopy, spots and stellar activity contribute a ton to these. And so understanding what stars look like is very important for that. Stephanie, how am I doing on time?
I forgot to start your time a while ago, but I think you have like 5 minutes left.
Okay, that's probably enough time. So I'm going to switch gears here, but still talk about information.
Oh, wait, does Will oh, you put down your hand. Sorry, Will.
Well, I'm going to just use 5 minutes.
Okay.
We can chat. We can chat afterwards. So switching gears a little, I'm not talking about planets and trying to figure out what planets look like, but still in the same vein of thinking about information theory. And I mentioned this at the beginning of the talk. It turns out that if you observe a phase curve of a planet in reflected light, its information content is actually huge. And so here is, this is a figure from another one of my papers earlier this year. This is the Earth seen at over a full year. It's the cloudless Earth, right? It's a spherical harmonic cloudless Earth. But this phase curve of the Earth is extremely complex, and the shape of the light curve changes with the season. And that's because you're going from crescent phase to full phase back to crescent phase. And that day-night terminator is essentially processing around the planet. And the amount of flux you're getting and the contribution from different parts of the surface is constantly changing. And so it's actually encoding different kinds of information about the surface of the planet at different phases. And you can see the little insets below each of the images of the Earth show the light curve over a single day at that phase. And so this is so much more rich in information than a single thermal phase curve, which would look the same,
of course,
every day.
In reality, you're going to be looking at the weather of the planet, not the surface features.
Yeah, exactly. So
this is also going to be time variable on day-to-day time scales.
Yeah. And so exactly. And that's going to be a huge thing we're going to have to deal with when we're able to do this with LUVOIR or HABEX or like the next generation of telescopes. But in fact, so I did this for the Earth a couple years ago based on scattered light in the background of TESS pixels. And I was able to see mostly at the clouds, right? Like you're not really sensitive to the continents because the clouds are the most reflective thing. And there was evidence of time variability as well. And so even if you can't use this to map the surface, you can learn about cloud coverage. Clouds tend to track continents. And the fact that clouds are always moving also helps, because if you observe for long enough, you can actually look at differences and try to like estimate what parts of the map are constant, which ones are variable. You can learn things about the clouds and the surface.
You're really making a lot of demands on that time allocation committee, aren't you?
No, for sure. This is a stretch goal, but I think eventually this is going to be a powerful way to probe the entire system, the entire planetary surface, atmosphere, thinking about it in terms of weather, climate, many years in the future. But the cool thing is that the information theory and the techniques are applicable now. I'll skip the slide. This is basically just showing how if you do inference on a thermal phase curve, you don't learn too much. If you do inference on a reflected light phase curve, you learn a lot. So I mentioned this is applicable now. So one of the pre-doc students from a couple from last year, Fran Bartolich, has been working with me on occultation light curves of Io. And so this is applicable in the solar system. So the top light curve there is Europa occulting Io, and then the bottom one is Jupiter occulting Io. And so Fran was able to use that to map the surface of Io and infer the positions of the active volcanoes. The bottom plot there was actually in a thermal phase curve, but in some cases, reflected light also matters. And so Mordecai, that's a good point, right? So mapping habitable planets or mapping planets like the Earth, we're decades away from that, and telescope time is going to be tricky. But like all these techniques are applicable now in the solar system to stars, etc. I'm probably out of time. Is that true, Stephanie?
Yeah, probably.
So 20 seconds just to talk about the coolest thing that I think I'm working on right now.
Well, take 35 or something if it's the
35.
coolest thing.
All right.
Yeah.
And that's oblate stars. And so this is something, there are a few examples of this. Kelt 9b is one of them, a hot Jupiter transiting a star that's spinning so fast that it becomes an oblate spheroid. And the cool thing there is that the transits are asymmetrical for two reasons. First, if the star is misaligned with the planet, you actually get different slopes on ingress and egress because you're transiting an ellipse, not a sphere, or not a circle. But you also get an intensity gradient because of gravity darkening. So the equator, the equatorial region of the star tends to be slightly cooler than the poles. And so you can use this to infer the actual three-dimensional architecture of the system. You get both the inclination and the obliquity of the star relative to the planet's orbit. And so there's a great probe of dynamics in planetary systems. Typically, the way people compute these light curves is numerically, by gridding up the surface, because it's hard. I mean, you're on the surface of an oblate spheroid, you have to integrate the area under the planet, which is bounded by an ellipse and a circle, and you're on this weird metric that's not spherical. This is our approach, is to actually try to compute those integrals exactly. This is a fun XKCD comic that was actually kind of useful in thinking about how to compute these integrals. But the punchline is that we were able to do this. So this is an undergrad that I'm working with, Shashank Dalakia, who's graduating Berkeley this year. And so we have fast, efficient, closed form solutions to the transit across oblate stars. So paper coming out soon. Keep your eyes open for that. I'm done. Thank you. Sorry, I went a little over.
That's fine. Thanks. Great.
My conclusion's up.
Great. We can definitely take time for a question if anyone has one, or of course you can always talk to Rodrigo afterwards. I'm gonna let Megan go first, Will, because you already had one, and then we'll get to you.
Yes, please.
Yeah, so Rodrigo, this is all super cool. So for the first topic of using an ensemble of many stars viewed at different angles to get information about the star spot statistics.
Yeah.
So if you start with an ensemble of similar stars that all have similar active latitudes and spot coverage and stuff like that, then you can infer that information. But how do you go about assembling that sample of stars that you expect to be similar in the first place? What sorts
Right. Yeah, that's a great question. The way I would do it, or the way that I'm thinking of doing it, is just narrowly selected bins in spectral type, rotation period, metallicity. Right. So the conclusion of your inference is going to be conditioned on your assumption that these stars are somehow similar being correct. If they're not similar at all, the model is flexible enough that you might get like a uniform or isotropic distribution in spot latitudes, right? So like the trick is making your model flexible enough such that one of your conclusions can be these stars, like the variance across these stars is very large. And so that in fact, that is something you could learn as well, right? So like, if we had, an infinite number of CPU hours, you could do this on all stars and find the space in which stars are similar by minimizing the variance in the inferred spot parameters. It would probably be some function of the things I said, right? So like temperature, spectral type, metallicity, et cetera. But in principle, that's something you could learn. I don't think you want to start with that. You want to start with assuming that all M9s with a certain metallicity are similar, but that can be expanded.
Cool, that's awesome. Good thing we're at CCA where we do officially have infinite CPU.
Yeah, and so exactly, yeah, and that's a stretch goal for me. Yeah.
Great. Will.
I had given up hope. Sorry, I had to get back to the mute button. I am just going to ask a very leading question, which I think I have asked you before, which is, have you thought about neutron stars?
Right.
They're much less interesting but every now and again turn up in the press, particularly these days with nicer.
Yes. And in fact, you put me on a thread with Tom, I forget his last name.
Riley, yeah.
Yeah. And I need to revisit that. I think it's a great idea. I am very interested. I'll add that to my list of projects.
I think this applies almost directly and would be huge in that
Yeah,
space.
and I am very interested in the information theory behind that. I think it would be really fun to think about. Yeah, thanks.
Great. Okay, Alberto.
Hey, thank you for the talk. I enjoyed it. I was wondering about your assertion of saying that the reflected light curves have much more information in them than the emission light curves. And I try to understand why. So what is a fundamental thing? There is a presence of the terminator in the reflected light curves, but you also have, there are similar terminator effects even in emission in many cases. No, there is a colder side and a warmer side. No?
Sure, yeah, and yes. The issue is that, so if the planet is emitting, equally from every point on the surface, the integral you're taking is just over the unit disk. And so there are too many degeneracies, right? So like you can't identify whether a spot is in the northern hemisphere or the southern hemisphere, they contribute equally. There are all sorts of like degeneracies related to the symmetries of where to put features. But if you have a part of the planet that contributes zero flux, you're now integrating over some strange loon-shaped feature. And it's much harder to identify ways in which you can identify degeneracies that give you exactly the same flux for a feature in a different position. The way that I think about it is like your limits of integration are now not non-trivial. And so they actually give you information. So for instance, at crescent phase, if you're at very, very close to crescent phase, all the information you're getting is about very, very high resolution features on the surface because they're just blinking in and out as they cross into that slight sliver that you're seeing. And so you're getting very local information. At full phase, you're getting global information. Everything's contributing. And for thermal phase curves, you're only ever getting this global information because the entire surface is contributing.
Okay, so it's sort of a mask aperture thing. So the masking actually gives you the extra information that you need.
Exactly.
And there is some masking in the infrared, but it's not as strong as you would like to have.
Right, yeah, so limb darkening limb darkening is another way that you're essentially masking features, but it is symmetric, it's not as strong, exactly.